Hello, and I'd like to talk to you today about an introduction to the generalized linear model. Now, the first line of Anna Karenina is a famous line. The novel begins with the statement that all happy families are alike, but each unhappy family is unhappy in their own way. During the course of the novel, we learn about an unhappy family. We have a better outcome here. We're going to learn about a happy family. And the theme of the generalized linear model, in fact, is that all regression analyses are a happy family. They're all basically the same. So you may ask, how are they all the same? A linear regression, a logistic regression, a Poisson regression? They seem different. What's the same? Well, let's look at what we do when we fit these different kinds of regression. So for a linear regression, we say that the expected value of our outcome, let's say lung function, for example, depends on some predictor X, perhaps age, in an additive way. There's some intercept, some baseline value, and then there's the effect of each predictor, age, sex, height, etc., and the effects of those are additive. They may not be linear, it may vary non-linearly with age, but in fact, the effect of age and the effect of height are additive. Now let's go to a logistic regression. To stay with my respiratory theme, suppose I was looking at yes, no, whether or not you had emphysema. Well, in that case, I do a logistic regression. And the logistic regression says that the logit, a transformation of the expected value of y, where y is now 0 or 1, it's not a continuous number, the logit of its expected value depends on a bunch of predictors, and the effect of each predictor may not be linear, but the effects are additive. There's an effect of pack years, and there may be an effect of gender, and there may be effects of other things. Now, of course, it might be that there's some effect modification, that there's an interaction between pack years and gender, and that's fine. I can put in another term on this right-hand side of the regression, that's pack years times gender. And the effect of that is additive to the main effect of pack years and the main effect of gender. Okay? So we can have interactions, but then every term adds up in predicting the logit of the expected value of y. Alternatively, another transformation of the expected value of y that will give you an outcome that is additively related to my predictors is the probit transformation. And I spoke about that when we were talking about logistic regression. And so we could do a probit regression also. Or suppose I am following these people with emphysema over time, and I am looking at how often they have serious exacerbations of their condition that require medical treatment. Well, that's a count. Some people didn't have any. In the follow-up period, some people had 1, some people had 2, some people had 3. And in that case, in a Poisson regression, I say some function, in this case, the logarithm of the expected value of y depends on, guess what? An additive function of predictors. There's a coefficient for gender, there's a coefficient for age, a coefficient for pack years, etc. There seems to be a pattern. This happy family is all the same A because the right-hand side of these equations are all the same. A plus B1, X1 plus B2, X2, etc. And they're all the same because the left-hand side is some function of the expected value of y. Now you may wonder about this one, but the identity function, right, is the identity function of x is x, so the identity function of the expected value of y is just the expected value of y. So I got that covered. The left-hand sides are all the same. The right-hand sides are all the same. The only thing that differs is what that function is. So the general paradigm for a generalized linear model is there's some function of the expected value of y that is additively related to a set of predictors. And that function has a name. We call it the link function. And because I would lose my voice if I kept saying the expected value of y all the time, we say mu, because mu sort of sounds like mean, okay? It's just a shorthand. It's the expected value, okay? So what changes between different kinds of regressions, they're almost identical except for G. But does anything else change? Well, let's go back to the hydrogen atom of regression. Let's go back to a simple linear regression. So here's a simple linear regression, and it has two parts. The first part is the part I care about, right? How does my outcome vary with my predictors? So that's B0 plus B1x. That tells me, on average, when x goes up by 1, y goes up by B1. Okay? But there's also an error, right? Because I'm never going to predict everybody's outcome perfectly. Okay? So E is about the error, and that tells us something else. It tells us how much y varies around its expected value. And you could have a lot of variance around the expected value or not so much variance around the expected value, depending on the R squared of your model. So all regression models also say something about the variance. They all have to make an assumption about the variance in order for you to fit the model. So what does this one say? In linear regression, we assume the variance is some number, well, let me call it sigma squared, sigma being the standard deviation of the error, and it's some number, and it's independent of the mean, and that means, on the one, it doesn't change with the mean. So that if I look at how much variability I have around the predicted value of my outcome, let's say lung function, when it's low, and when it's high, I want the variability to be constant, because that assumption is implicit in the computer program that gives you your coefficients, because your computer, your linear regression model, your statistical model, assumes a constant variance and uses that assumption to estimate the B's. Now, for logistic regression, and essentially any other kind of regression, the variance is not independent of the mean. The variance of a 0, 1 variable is p times 1 minus p. So let's think about that for a minute. Suppose I have a population and 10% of them have the outcome on average. Then my p is 0.1, and p times 1 minus p is 0.1 times 0.9, which is 0.09. But what if p is equal to 0.5? Then I get 0.5 times 0.5, and that means that the variance is equal to 0.25. So if I have a high prevalence of some outcome, I'm at, say, the high end of my predictors range, and so they're predicting, yeah, there's a pretty good probability of this thing happening, the variance around that is going to be bigger. So in general, the variance is some function of the expected value, because mu is p for binary data, okay? And so to tell a generalized linear model program what regression to fit, what differs from regression to regression is G and V. Well, that's great, and it's really cool that statisticians figured it out, and that you can give a G and a V, and then, all other than that, all the regressions are the same, but, so what? What does it do for you? You already can use proc logistic to fit a logistic regression, and another model to fit a linear regression, etc., etc. Okay, I can put them all together in one function. So what? So let's answer that by going back to why we're doing these regressions. We're doing these regressions because we would like to know if an exposure is a causal factor for an outcome, and if so, we'd like to know how much of an effect it has. Now, if there was no such thing as confounding, life would be easy. But we worry about confounding, and therefore we need to fit regressions because we need a control for all those confounders. And we go out and we collect those confounders. And what we normally say is that if I have no omitted confounders, and if I've modeled the outcome confounder relationship correctly, of course, if you do propensity score models, then you're going to make a different assumption, but let's just take standard epidemiology for a moment. So I model it correctly. That means, yeah, I may have measured the confounder, but if I put it in as linear and it's not, I could still be confounded. If I omit an interaction, I could still have confounding. But if I've modeled it correctly and I have no omitted confounders, the association in a standard outcome regression should be causal. Now, more likely, we would argue that if we have no omitted important confounders and we did a pretty good job of modeling the outcome confounder relationship, we're probably okay. And then when we talk about things, we get, well, there's another way to do it with inverse probability weighting and things like that. We're not going to talk about that here, but there's something that's left out of this dialogue, and that's the statistical model. You also assumed, if it was a continuous outcome, that doing a linear regression, which assumed that the variance was constant, was correct, and assumed that the distribution of the errors was normal. And our inferences are also conditional on some of the assumptions we make about each of these different kinds of regressions that we fit to different kinds of data. What if they're not met? Then we're also going to get potentially biased estimates, biased confidence intervals. We can reach the wrong conclusion. Generalized linear models give us an opportunity to relax these assumptions and get valid inferences. They let us do that for all the different kinds of regressions we have. They let us substitute one generalized linear model for another when it's more appropriate, and they let us relax even the assumption that I know what the distribution of the data looks like and still get valid inferences. And they can do it for all these different kinds of regressions because they're a happy